Okay, so we started looking at graphs and the end behaviors of graphs by looking at the limit as x goes to infinity or negative infinity, and then also looking at asymptotes and what we're going on with vertical asymptotes or horizontal asymptotes. And so I wanted to just go back and kind of review a little bit of algebra with you guys on how to find the end behaviors of a function. So that's basically what we're doing when we're looking at the limit as x is going to infinity and negative infinity. So let's first talk about polynomials. And so polynomials, the end behavior of a polynomial function is the behavior of the graph of f of x as x approaches positive infinity or negative infinity. And so mathematically, we have that, and we could write this as the limit, right, as x is approaching infinity of f of x. Or if we're looking at the other direction, as x is going to negative infinity of f of x. So when we're looking at the end behaviors of our graph, what's going on as your x value goes to positive infinity or negative infinity, there's a couple things that we have to look at when we're looking at a polynomial. And so we have to look at the degree of our polynomial, and we have to look at the leading coefficient of that polynomial. And by that, looking at the degree and the leading coefficient, there's 4 different possibilities that could happen. That will tell us what's going on with the end behaviors of our function. Okay, so to predict the end behaviors of a polynomial function, first check whether the function is an odd degree or an even degree, and whether the leading coefficient is positive or negative. So I just kind of wanted to go through really quickly again, if you forgot, the definition, formal mathematical definition of a polynomial. So recall a polynomial function in the variable x with a degree n is defined as the following. And so p of x is equal to a sub n all raised to the x to n power plus a sub n minus 1, x to the n minus 1 power plus a sub n minus 2, x raised to the n minus 2 power plus dot, 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 plus a sub 2 x squared plus a sub 1 x plus a sub 0. So that looks a little daunting sometimes, especially the first time that you see this, but all this is saying is this number in front of, or this a sub I, that number in front of your variable x, this is contained in the real numbers. So mathematically, this kind of funky e means contained. And that r with the kind of 2 vertical lines to make that capital R, that means the real numbers. Okay. It tells us that a sub n can't be 0. The reason why that's the case is if this was 0, then really our degree is not n anymore. Our degree would be the highest power, which would be n minus 1. So they put that little stipulation on there. And then n, our exponent of our variable, n is a whole number. So recall, whole numbers are in the form of 0, 1, 2, 3, going on forever. Okay, so just kind of a little quick review of a polynomial and finding the end behaviors of the graph. So again, we want to look at just the degree and the leading coefficient, and that just one term gives us what's going on with the graph. And once you look at the degree, you're determining, is that degree an odd number or is that degree an even number? Is that coefficient in front of it positive or is it negative? So let's look at the 4 different cases. And so let's say that a sub n, we have 2 different cases. We're either going to be a positive number or a negative number. Let me move it down. And then we have n, which is our degree. And we're looking at the degree and we want to know, was this even or odd? Okay, so let's make this table here. And let's look at the 4 different cases. And a sub n, again, is our leading coefficient. And so let's look at the limit as x is going to positive infinity of a sub n x raised to the nth, where this is a positive number. Let's say n is even. So when I'm doing this, I kind of try to think about, okay, if I'm plugging in numbers that are going to infinity, I know that they're positive numbers. I'm really trying to figure out when I multiply that number, that positive number raised to any power is always still going to give me back a positive number. And if I multiply it to this positive coefficient here, I'm just trying to figure out, is that result going to be positive or negative? Well, positive times a positive is positive. So this has to shoot up to positive infinity. And so here, as I'm going off to positive infinity, x values, this shoots upwards. So let's look at this now, same scenario, but this time the limit is x is approaching negative infinity of a sub n x raised to the nth power. So now I think about it, I think infinity looks funky, but I think about it and I think, okay, now I'm plugging in negative numbers. I'm raising it to an even power. Well, if you multiply a negative number, an even number of times, that's positive. So now I know I have this result that a sub n, I was given, or I was told that that was positive, times this negative number going to negative infinity, but that negative number raised to an even power is positive. And so positive times positive, I know that that result is going to positive infinity. And so the end behavior shoots upwards here. So that was one case scenario. Let's look at it when a sub n is negative and our degree is even. Okay, so I'm looking at the limit here. Maybe let's go left to right. So negative infinity of a sub n x raised to the nth. And again, a sub n, we're going to say, is a negative number. So negative coefficient in front. And n is even. So I'm putting in a negative number. I'm raising it, multiplying it an even number of times, which means this negative number raised to the nth power is going to be positive. And then I have this negative coefficient out front. So I have some negative number all times some positive number. And I know that result, negative times positive, is negative. And so as x is going to negative infinity, this is shooting downwards. So I do the same thing, kind of reason with myself if I'm going to get back a positive or a negative number as x is going to positive infinity. So a sub n, we're given in this case, was negative, and taking a positive number and raising it to any power, positive times itself, an even number of times or an odd number of times is always even. I'm sorry, positive. So we have negative times positive, which is negative. So this shoots down to negative infinity. So you kind of go through that reasoning with each type. So odd, if I'm looking at an odd power and a positive coefficient. So as x is going to negative infinity, a sub n x to the nth. This time we're going to say a sub n is positive. It's a positive number. And n in this case, we're going to say is odd. So we have this positive coefficient times, now taking a negative number, plugging it in and raising it to an odd number of times. So multiplying negative number and odd number of times is negative. So we have a positive times a negative, which is negative. So this is going to go to negative infinity. As x goes to negative infinity, our y value shoots downwards. It goes to negative infinity. And then the limit as x goes to positive infinity. Again, a sub n, this time we're going to say is negative. Oops, I was going to do a different. Actually, I'm not done with what I was doing. I haven't looked at positive. Okay, so a sub n times x to the n. So a sub n again is positive. Any number raised to any power that is positive raised to any power is positive. So we have a positive times a positive, which is going to positive infinity. So it's shooting upwards. Okay, so last case scenario, we got a odd degree and our coefficient is now negative. So limit x goes to negative infinity of a sub n x raised to the nth, and a sub n was negative, and n is going to be odd. So a sub n is negative, it's going to remain negative, times, well, if I take a negative number raised to an odd power, that's going to be negative, and a negative times a negative is a positive. So this goes to positive infinity. So as x is going to negative infinity, our graph shoots upwards. And then the last case where a sub n is negative and n is odd, going to positive infinity. Well, a sub n we said was negative. All times a positive raised to any power is positive. This goes to negative infinity. So it shoots downwards. So really, if you're just given a polynomial and you're asking for the limit as x goes to negative or positive infinity, the graph is either going to shoot up or down, go to positive or negative infinity at those end behaviors, but it all depends on that leading coefficient and the degree of that polynomial. If you added any more terms to that, it doesn't matter, that's not going to affect the graph. You only need to look at that one term to help us figure out what's going on to the end behaviors. So that was a kind of a quick review just on polynomials and looking at what's going on as x is going to positive or negative infinity. But let's look at other scenarios that we could have. Maybe before I do that, let's see if you guys have any questions. Okay, so we're looking at tools that we've learned in algebra to help us graph and just kind of reviewing. And so now let's look at a different type of function. How about an exponential function? So recall for an exponential function, maybe we have y is equal to a times b raised to the x power. We had to have a stipulation on our base here. B could not equal, or actually B has to be greater than 0. But it can't be 1. If it's equal to 1, then it's not an exponential function. And so recall, there was a couple of different things that could happen with your exponential function. It depended on your b value. So if b was between 0 and 1, your base, your graph looked like the following. And I'm going to say here that because coefficient in front actually could flip things. So I'm going to just say that in this case, a is greater than 0. Okay, so if we look at this, we can tell what's going on with our limit, right? Let's look at our end behaviors here. As the limit of our exponential in this case is going to negative infinity of b raised to the x power. This is going to equal, this is shooting upwards. It's actually not going to any one y value. We actually would say the limit doesn't exist, but here it's shooting upwards and we want to know what's going on with the graph. So we're going to say that this is going to positive infinity. If we look at the exponential function where your base is a number greater than 1, recall that when you graphed your function, maybe I should go back to this other exponential really quick. Let's look at the limit as x is going to positive infinity in this case. So in this case, if I'm looking at my graph and as x is going to positive infinity, right, my y value is getting closer and closer to 0. It's never going to equal 0, but it's getting closer and closer to 0. And so the limit as x is going to positive infinity in here is equal to 0. Okay, so now looking at y equals b to the x or a times b to the x, where b is greater than 1, and our, again, value a is greater than 0. If we looked at the graph of this function, and this is the normal shape of what it looks like, it might be growing steeper depending on what your base is. But this is the general shape. And if we look at this as a limit, right, as x is going to negative infinity of a times b to the x, and this is going to 0. And the limit as x is approaching positive infinity, our y value is shooting upwards and it's never getting to any particular y value, but it's continuing to grow positive to positive infinity. Okay, so you just got to be kind of careful because transformations of graphs, remember, if you added a number outside of the function, that moved our graph up or down. And so our horizontal asymptote, this is a horizontal asymptote, is going to change if we have transformations of our graph. That coefficient in front of the exponential piece, if it's negative, remember that's a reflection. That's changing our sign of our y. That would be a reflection across the x-axis. And so that could also affect the graph of where the asymptotes are, the horizontal. So exponential functions, one. Another function that you should be familiar with are your logarithmic functions. And logarithms, you guys, are going to be some of our best friends. They're going to actually take things in this class that are really complicated and would be so ugly to do and break it down so it's so simple. And so, and we'll go over rules of logarithms later, but let's look at their graphs now when we get to that piece. Okay, so let's say f of x, right, is equal to log base b raised to the x. I'm sorry, log base b of x. So exponential form, basically, this is saying we're trying to figure out what our exponent is that we would raise our base to get back x. So another way to write this is b to the f of x is equal to x. So a couple of rules for our log functions. Our base, it has to be positive and it cannot be 1. We also have some rules on our domain in this case. Our domain, our value here, what the log we're taking, log of the base we're taking of, that has to be bigger than 0. That argument in here, whatever it is. And so looking at this, it depends on, is that base between our 0 and 1? Or is our base of our log going to be bigger than 1? And so if we have it where b is between 0 and 1, oops. Let me think about it. Our graph is going to look like this. So notice it's not, our graph does not extend past x equals 0 to the left. There's no values of x in here, which actually are 0 or negative. So our domain is positive. If we look at the limit here, as x goes to negative infinity, this is actually undefined. We can't take a log of a negative number. We can say, though, that the limit as x is going to positive infinity of f of x, this kind of looks like it's leveling out and it might be a horizontal asymptote, but it's not. It's going to just continue to go down. And so this is equal to negative infinity. But we were talking about vertical asymptotes yesterday. And so notice that our logs have a vertical asymptote. And so we could say that the limit as x is approaching, so notice that we're only approaching one side of 0. So, and if I look at this, I am approaching from the right-hand side of 0. So I would write this as a limit as x is coming from 0 of f of x on the right. This is going to positive infinity. And then the other case that we could have, when we have our log, is y is equal to log base b of x, where b is greater than 1. Okay, so if we looked at that, our graph looks similar. It's kind of reflection, but it's more like this. And so again, this is undefined as I go to negative infinity. And if I look, though, as x is going to positive infinity, so limit as x approaches positive infinity of this value, just call it g of x. This is going off to positive infinity. And again, I can say the limit as x is approaching 0, but I'm coming in only on the right-hand side of g of x. This is a vertical asymptote. This is going towards negative infinity. Trying to think if there are any other functions. What about your sine or cosine function? If we were looking at end behaviors of our sine and cosine function, is it ever going to any particular number? Or is it ever going to shoot off to positive infinity or negative infinity? So for instance, let's look at y equals, or f of x equals cosine of x. So if you remember what the graph looks like of cosine of x, it's just a wave. Cosine, when x was 0, started at 1. Pi halves, we got down to 0. At pi, we had -1, right? 3 pi halves back up to 0. And then at 2 pi, we hit 1. And that was one period of the wave function. But this continued on forever, right? Like this. And same thing over this direction. Okay, so can we say that the limit, can we look at, does it exist? The limit as x goes to negative infinity of cosine of x? So with polynomials, even though the limit didn't exist as x went to positive or negative infinity, we could tell what it was going towards. It was shooting up either positive infinity or shooting down to negative infinity. This graph, and same thing with sine of x, is a wave, and it's bouncing back up and back and forth between y equals -1 and +1. And there's no value as this goes on forever that it's approaching. And so when we're looking at the limit of our trig functions of cosine of x and sine of x, those do not exist. So similarly, I can say the same thing with sine of x. When you're looking at, how about your radical functions? So y is equal to, I don't know, the nth root of some function f of x. Well, it really depends. In here, what's going to happen? We have to be careful. We need to look at pretty much the leading coefficient and the degree under here. And we also have to be worried about what this number is. If this is odd, then f of x has no stipulations. I can have a negative number underneath an nth root of a radical. I can take the cubed root of -1. I can take the fifth root of a negative number, etc. If those are odd, this can be any value. So f of x. The domain or range. But if I was looking at y is equal to the nth root, how about, let's call it mth root of g of x, and m was an even power index, then we have to be careful. We have to limit the domain. And so we have to say, well, in order for this to be the case and get back a real number, g of x has to be greater than or equal to 0. Let me see if I can pull an example of looking at a limit and behaviors with a radical. Before I jump into, like I said, an example with a radical, and I wanted to do one that was not rational. So there was just a radical and there was nothing in the denominator but 1. It's helpful that we talk about rational functions again really quick. And so I did talk about it in somewhat detail and review yesterday about vertical asymptotes and horizontal asymptotes. And so vertical and horizontal asymptotes occur or can occur if we have a rational function. So recall rational functions those were in the form where you had some p of x, some function in the numerator, all over, let's say q of x, some function in the denominator. And so depending on a couple of things, we can have vertical asymptotes. And so what would happen here is I'm looking at the limit as x is approaching some value, some x value of a, of this p of x over q of x. This can either go to positive infinity or negative infinity. And so if I was looking at this graphically, a couple of different things could happen, but let's say we had a vertical asymptote here at x equals a. Let me move a over. As we're getting closer to x equals a on the left-hand side, it can either be shooting upwards, so the graph could be shooting upwards like this, or it could be shooting downwards like this. But it's never, as we're getting closer and closer to the vertical asymptote, it's either going to be going to positive or negative infinity. Same idea, as we're approaching a on the right-hand side, it's either going to be shooting upwards or it's going to be shooting downwards. So we could have opposite directions, one's up, one's down. They don't have to be going in the same direction on the left and the right. So those limits really don't exist. But again, we tell you that if it's positive or negative infinity, so we know what's going on with a graph there. And so recall that there was a way to find vertical asymptotes. And vertical asymptotes had to do with the degree of the, sorry, that was horizontal. Vertical asymptotes have to deal with what sets the denominator equals 0. So to find these, find all values that set the denominator equals 0. But not also the numerator. If it sets both of them equal to 0, recall we looked at limits of the type where we had a rational function and we plugged in a value of x and we got 0 over 0. If we had gotten that form, that was an indeterminate form, and so we had to rewrite it, we had to factor it and cancel like factors. And we found then when we did that, our limit actually did exist. It wasn't defined there in our function, but the limit did exist. There was actually a hole in the function. So if it sets both the numerator and denominator equals 0, it's not a vertical asymptote, it's a hole. So, but not also, let me go back and finish what I was writing here, but not also the numerator. Okay, so vertical asymptotes, we're approaching some x value, x equals a, and it's shooting up to positive or negative infinity as we come in on the left and the right. And then horizontal asymptotes, that had to do again with the degree of the numerator and denominator. Maybe y equals p of x all over again q of x. How about n equals the degree of the numerator? And let's say that d equals the degree of the denominator. And so there's 3 different cases that could happen. Your degrees could either be the same, so n equals d. Basically, you're going to have a horizontal asymptote. Could be above or below the x-axis, but let's just put it above the x-axis for now. And this line can be found. It's y equals a divided by b, where a equals the leading coefficient. I'm going to just say LC of the numerator. And b equals the leading coefficient LC of the denominator. So what's happening as we're going to positive or negative infinity, that graph is going to get closer and closer to that horizontal line. It's possible it can cross it, but it will still hug it. So you might have something that looks similar to this. So that's if they're the same. If they're not the same, the degrees, maybe the degree of the denominator is larger. So D, that degree of the denominator is bigger than N. If that's the case, this is our HA up here, then we do have a horizontal asymptote, and it's our x-axis. And so we have here that y equals 0 is the horizontal asymptote. So again, as we're going off to positive and negative infinity, our graph somehow is growing or getting closer and closer to the y value of 0. It's possible to look like this. So limit as x goes to positive, negative infinity, our graph p of x over q of x is equal to 0. We're up here, we would write it mathematically with limits. The limit as x is going to positive or negative infinity. That y value that we're getting closer and closer to is that leading coefficient of the top over the bottom. And then the last case scenario was if the degree of the numerator was larger. So the degree of the numerator, n, is bigger than the degree of the denominator, d. If that's the case, then there is no horizontal asymptote. We can figure out, is it shooting off to positive or negative infinity? But it's not going to go towards one y value. And that would have to do with us, is it shooting off to positive or negative infinity, with looking at the let's say x raised to the degree of the numerator was bigger. So numerator minus the degree of the denominator. So we would look at this, is this even or odd? And we would actually look at the leading coefficient of the top divided by the bottom. And we would determine, is this number going to be positive or negative? So like we were talking about the end behaviors of our polynomial function, that would be the same thing that we would do to see if it's going to positive or negative infinity if the degree of the numerator was larger. So we talked about one important limit, and that would be helpful for us to look at these end behaviors of our graph of a rational function to see if it had a horizontal asymptote or not. So we said yesterday that the limit as x goes to infinity we can actually extend that to plus or minus infinity of 1 all over x raised to the nth power. I need to put on a stipulation that my exponent down here is positive, because if it's not positive, rules of exponents, remember, we would bring that up into the numerator to make it positive. So if this is the case, and n is a number that's bigger than 0, then this value here is going to go to 0. If you have any number, so any number here, and dividing by x, and you're plugging in positive numbers going to positive infinity, this is blowing up huge. So 1 over a huge number, any number over a huge number that keeps on getting bigger, goes to 0. Same thing with negative infinity. Doesn't matter. It might be a negative y value that's getting closer and closer to 0, or a positive y value getting closer and closer to 0. But we're going to use this fact, or we can use that fact to help us find those horizontal asymptotes. So let's look at an example now.